Take a good look at this image. This is the Crab Nebula. It's what's left of a giant star that exploded almost 1,000 years ago. Now, it's thousands of light years away from us, yet somehow we know it's full of things like sulfur and oxygen. So how? How in the world do we know the chemical makeup of something so unbelievably far away just by looking at it? Well, the answer is all wrapped up in the nature of light itself. And it's a story that turned our entire understanding of the universe completely upside down. Let's start back in a time when we thought we had it all figured out.
You know, it's kind of funny to think about, but by the late 1800s, scientists felt pretty good about themselves. They thought they had the universe basically solved. As far as they were concerned, everything fit into one of two neat little boxes. You had matter, solid stuff made of particles, and then you had energy, which traveled in waves. Light, for example, was a wave. Everything had its place, nice and simple.
Now, they didn't get to this tidy picture easily. For centuries, there was this massive debate. In one corner, you had the giant, Isaac Newton, who was convinced light was a stream of tiny little particles he called corpuscles. And in the other corner, you had Christian Huygens, who argued, nope, it's a wave. This argument went back and forth until the early 1800s, when a guy named Thomas Young performed his now famous double-slit experiment. He showed that light creates these interference patterns, where waves add up or cancel out, and that's something only waves can do. That was pretty much the knockout punch, and the debate was finally put to rest for good when James Clerk Maxwell proved mathematically that light was an electromagnetic wave. So, by the end of the 19th century, the scorecard was pretty clear. The whole particle idea? Discredited. It just couldn't explain things like interference. But the wave view? It was the champion. It explained everything they could see: reflection, refraction, and especially those interference patterns. It just worked.
And that was that. Seriously. The science was considered settled. The universe was made of particles of matter, and light was a wave. Done. Case closed. But, as it turns out, the universe had a few more secrets up its sleeve.
So, just as scientists were kind of taking a victory lap, a few weird problems started to pop up. And these weren't just small rounding errors. They were deep, fundamental paradoxes that the physics of the day had absolutely no answer for.
The first major crack in this perfect picture had a name that sounds like it's straight out of a disaster movie, which tells you just how big of a deal it was. The ultraviolet catastrophe.
So this catastrophe came from studying something called black body radiation. It sounds complicated, but the idea is actually pretty simple. Just imagine heating up a piece of metal in a fire. As it gets hotter, it starts to glow, right? First red, then orange, then bright white. A black body is just the scientific ideal of a perfect version of that glowing object. And scientists wanted to use their perfect wave theory to predict exactly what colors of light it would give off. And this is where the wheels completely fell off. What's so amazing here is just how clear the problem was. For long wavelengths of light, like infrared, the classical wave theory worked perfectly. The predictions matched the real-world data. But when they looked at the shorter wavelengths, like ultraviolet light, the theory predicted that the energy should shoot up to infinity. In reality, of course, it didn't. The intensity dropped off to zero. This wasn't just a little bit wrong. It was spectacularly, fundamentally wrong. This huge problem just sat there for years, completely unsolved, until a physicist named Max Planck came along. Around the turn of the century, he found a solution. It was a mathematical fix that worked perfectly, but the idea behind it was so bizarre and radical that even Planck himself hated it.
Planck's idea was, what if energy isn't smooth and continuous? What if it can only be given off or absorbed in tiny, distinct chunks? He called these little energy packets quanta. And when he plugged that single, strange assumption into the equations, the ultraviolet catastrophe just vanished. The math suddenly matched reality perfectly.
And right here, this is the crucial point. This idea of quantization. Think of it like this. Classical physics saw energy as a smooth ramp. You could have any amount of energy just by being at any point on the ramp. Planck was saying, no, at the tiniest level, energy is a staircase. You can be on step 1 or step 2, but you can never ever be halfway between steps. This simple, crazy idea was the birth of quantum mechanics.
Okay, so Planck had solved one huge puzzle. But there was another one, still baffling scientists, something called the photoelectric effect. And who should step in to solve it but a young Albert Einstein, who took Planck's radical quanta idea and just ran with it.
So here was the puzzle. When you shine light on a metal plate, sometimes it knocks electrons loose. The old wave theory said that a brighter light, a more intense wave, should hit the electrons harder and send them flying off faster. But that's not what happened at all. As you can see, you could shine a dim, high-frequency blue light, and bam, electrons were ejected instantly. But you could blast the metal with a super bright, low-frequency red light, and nothing. Changing the brightness only changed how many electrons got knocked off, not how fast they were going. For a wave, this made zero sense. Einstein's stroke of genius was to take Planck's idea and push it even further. He said, what if light itself isn't a continuous wave, but is actually made of a stream of these little energy packets? We now call them photons. And in that view, everything clicked into place. Each photon is like a tiny bullet. A high-frequency blue photon is a high-energy bullet. It hits an electron hard and knocks it flying. A brighter light just means you're firing more bullets, which knocks more electrons loose. But each hit has the same amount of oomph. And this created a whole new crisis. One experiment, Young's double slit, proved without a doubt that light is a wave. But this other experiment, the photoelectric effect, proved it was made of particles. So what gives? They couldn't both be right, could they? This led everyone to the ultimate mind-bending question at the very heart of this new physics. What is light, really? Is it a wave, or is it a particle? The evidence was just completely contradictory. I mean, if you set up an interference experiment, light acts exactly like a wave 100% of the time. But if you set up a photoelectric experiment, it acts just like a particle. It was as if light decided what to be based on the experiment you were running. The answer that physics, finally, reluctantly had to accept is one of the strangest and most profound truths about our reality. Light isn't an either-or, it's a both-and. This is what we call wave-particle duality. Light's secret identity is that it has two identities. It is somehow, simultaneously, both a wave and a particle. Now, this might sound like some weird philosophical head-scratcher, but trust me, understanding this bizarre duality is the absolute foundation of almost all of our modern technology. Let's see how this strange quantum idea shows up in our everyday lives.
Every single one of these things, the radio waves that carry signals through the air, the microwaves in your kitchen, the Wi-Fi that's probably connecting you right now, even the X-rays at the dentist's office, they all operate on these quantum principles. Our ability to build this technology comes directly from understanding light's weird dual nature. And this brings us right back to where we started. It's because we understand this secret identity that we can analyze the light from the Crab Nebula, decode its message, and know exactly what it's made of.
So, if there's one thing to take away, it's this. That neat, tidy, solved universe of the 19th century, well, it was an illusion. The real universe is far stranger, far more mysterious, and frankly, a lot more interesting. And it really makes you wonder, if something as fundamental as light can hide a secret identity like this, what other incredible secrets is the universe still waiting for us to discover?